Okay, so let's go into Unit 2, Molecular and Ionic Structure and Properties. Again, should be about 12%. So, types of chemical bonds. You should be able to tell if something is ionic or covalent. You should be able to tell if something is polar or nonpolar. These should be about valence electrons and pretty straightforward. The difference in electronegativity is not the only factor. You also have to work about geometry and whether or not those are metals and nonmetals. If it is a metal and nonmetal, it's more likely to be ionic. If it's two nonmetals, it's more likely to be covalent. Metallic bonds, you have to remember that those electrons are not discretely assigned to individual atoms. They are considered to be delocalized, that the atom nuclei and the core electrons for the atoms are floating in a sea of electrons, so to speak. No one electron is associated with any individual atom. Intermolecular forces and potential energy. As we get, you should be able to identify a graph with potential energy, and the one I typically show you is two hydrogen atoms that are infinitely far apart. As we move them closer together, the energy of the two atoms begins to decrease, and we get to a potential that is the lowest energy, and that's the ideal bond length. If we push them closer together, the energy goes back up, and if we pull them apart, the energy goes up. And this is to maximize Coulomb's attractions without increasing Coulomb repulsions. And those repulsions would be nuclei to nuclei, electron to electron. The attractions are electron to nuclei of the other two, nuclei of one atom to the electrons of the second atom, etc. Structure of ionic solids. It is an array of cations and anions that are systematic, three-dimensional, maximizes the attractive forces while minimizes the repulsive forces. So you want the cations as close to anions as possible without anions or cations being next to each other. And this again is consistent with Coulomb's law, has to do with packing, how big are the nuclei, how big are the ions and how closely can they pack. They do not ask you for packing structures, though. Structure of metals and alloys. Metals are, as I said before, a sea of electrons surrounding the cation, that is nuclei and the core electrons. There are two types of alloys. Alloys are a mixture of two or more elements, one of which must be a metal, the other may be a metal or a nonmetal. Something like carbon steel is iron with carbon atoms and a few other things, and that would be an example of an interstitial alloy. And then the other type of alloy is called a substitutional alloy, and that would be like brass, where you would have copper with zinc inserted or replacing copper atoms because they're about the same size, so one can replace the other. Interstitial is something where they are vastly different radii, and they are in between the spaces, interstitial. Okay, Lewis diagrams. God bless, draw the Lewis diagram. Figure out how many valence electrons there are. When you're drawing a bonding model for something, make sure you include lone pairs. You want to maximize the space around the nuclei or decrease the amount of repulsion between the electron pairs. So that's why we get certain shapes. They can be constructed according to an established set of principles. We've gone over those. If you need a refresher on that, let me know. I think I have some videos already online on that. So, resonance and formal charge. When you're drawing a Lewis structure, you want to account for resonance. So if you see a double bond and lone pairs, there is likely resonance. If you see formal charges and you should know how to write out formal charges, you would want to minimize those formal charges before completing your Lewis structure. The octet rule applies to the first and second row elements and can be violated for anything in the third row or below. And that is because now in the third row, n equal to 3, we now have d orbitals available that we can use to hybridize electrons. You typically will not be asked hybridization with anything with d orbitals, but just keep counting. If you used up your 1s and your 3p's and start adding d's till you get to the total number of bonding regions. And one bonding region could be a single bond, a double bond, a triple bond, or a lone pair. So lone pairs are not hybridized, but they are in unhybridized orbitals. Vesper hybridization. See, there's a lot of stuff here, and I urge you to read it all. It says specifically that hybridization will not be addressed in the AP exam when an atom has more than 4 pairs of electrons surrounding the central atom. So you don't need to do d orbitals, and there's a confirmation of that. So, Vesper theory, Coulombic repulsions are being reduced. You should be able to draw Lewis structures. The ideas that you may have to address would be molecular geometry, bond angles, relative bond energies, relative bond lengths. Multiple bonds are shorter than single bonds. Presence of a dipole moment, in that you would have to look at its molecular geometry to make sure those individual dipoles did not cancel, and hybridization of the central atom. So, I will, Unit 3 is huge. It may have to be divided into 2 sections. I think there's like 12 or 13 points in Unit 3, and that's also why it's a larger percentage. Okay, thanks.